All right, logicians, I want to talk to you about not chapter 9, section D of your Baronet textbook. And this is the very brief section that talks about conditional proofs and indirect proofs when you're working with quantifiers. And there's actually almost nothing new or interesting to say about conditional or indirect proof when it comes to quantifiers. Everything works the same as you would expect it to, except that there is one restriction that we have to put on the universal generalization rule. And here's what that restriction is. Universal generalization cannot be used within an indented proof sequence if the instantial variable is free in the first line of that sequence. Now, here's an example of what they mean. Remember, a free variable is one that is not bound by a quantifier, right? So if you look at, here's line 2 is the first line of the indented proof sequence, assumption CP, and it's CX. Now that's a free variable. It's not bound. There's no quantifier that binds that. And that means it violates, well, if you then, in line 3, if we try to do universal generalization from that, which you would ordinarily be able to do if you've got CX, and you could say for all X, CX, but it violates this restriction. And you might think, well, why is that, that we can't use UG, universal generalization, in this sequence? And the issue is this. In this case, the free variable isn't just naming any old arbitrary individual. The free variable names an individual that is assumed to have a particular property. So if that doesn't make sense, just memorize the rule. If you can't, if you've got a free variable on the first line of this indented proof sequence with the assumption, you can't do universal generalization on that. So bear that in mind. Okay, that's it though. Now, let's look at an example of a good way to do a conditional or indirect proof in our next slide here. So the premise we're given is premise 1, for all x, if x is f, then x is g. In other words, everything that is f is also g. And the conclusion we're supposed to get is, if everything is f, then everything is g. And you can kind of intuitively see how that is. You know, well, yeah, I won't try to explain it. So, but here's the way we could do it. One way to do it is with conditional proof sequence, right? Because the conclusion we're trying to get is a conditional statement. So if we're going to use conditional proof, then the first line of that is going to be assumption CP. Okay, the assumption is going to be the antecedent of the conditional statement which we are trying to prove. So in this case, the antecedent is for all x, x is f. And then the conclusion of the indented proof sequence that we're going to be going for is the consequence of the conditional statement that we're trying to prove. So the conclusion of the indented proof sequence should be for all x, x is g. So the way we do it is we assume this. Now, what are we going to do? Well, as per usual, we're going to have to drop out the quantifiers probably in order to work with things, because you can see that what we want to do is this. If we know that everything that's x is f, and everything that's f is g, then we know that, sorry, this premise here says, if we know that everything is f, and we know that everything that's f is g, then we know that everything's also g. Like, you can see how that works. So we're basically going to drop out the quantifiers and do modus ponens. All right, so the first step here is universal instantiation on line 1. And we say that if x is f, then x is g. And then we do universal instantiation on line 2. We get x is f. And then we can do modus ponens on 3 and 4. We get x is g. And now we can do universal generalization again. And we get for all x, x is g. And that's what we were going for. Now pause right here. Why was it permissible to use universal generalization in this indented proof sequence? Did we violate the restriction? No, we didn't. because this was not a free variable. X is not a free variable on the first line of the indented proof sequence. It was a bound variable. It was bound by the quantifier for all X. So it was permissible to use universal generalization here. And now we finished our proof sequence. We can discharge it. The conclusion we want is if for all X, X is F, then for all X, X is G. That's how we use universal generalization with an embedded proof sequence with quantifiers the correct way.